All right. So my big question is, what's the deal with charge? Yes, because it seems to be for humanity, that's the number one thing that we have interactions with. It's powering basically just this recording right now, this microphone right now. It's something that we have the ability to harness, but are there areas that we haven't explored? And just based upon this geometric model right here, if you have charge itself basically wrapping around that mass boundary, just going on with a periodic table, it's like, well, that's what a lot of chemistry is. The interaction between these charges with what we consider electrons and how they interact, how the different elements come together, they bind together, how they'll break apart and everything. That's basically where I'm at right now. I'm just trying to conceptualize in my mind what's actually going on here. Because it's like, okay, we have something like this. It's like, okay. It's terrible drawing there. But essentially, kind of get, it's like, okay, it's basically this. This right here. This two-dimensional form here. So I'm thinking, I'm like, okay, this Giesecke manifold, the first homology group is the integers. It's very interesting. Charge just seems so essential to what's going on in just us being able to not fall through the floor, just utilizing Pauli exclusion principle. And just as we know, or at least has been theorized, if you exceed a certain amount of whether it's gravitation due to whatever curvature or mass or something like that, once you start going past that, things seem to get all wonky there, and just that's basically just my initial thing. So, Dad, do you want to kind of go into it? Or Kevin, do you have any thoughts?
No, I'm kind of listening though.
I'm just.
Listening.
Well, that's the thing. These are just some of the questions that I've had that I've just been pondering in my head, and hopefully, Dad has some intuition.
I guess I'm going to need you to talk back during
Okay, yeah.
what I'm doing up here too, because do you feel like you have a much better sense of an answer if I swap out charge with time?
No.
What about space?
Warmer.
Okay, space you feel better on. How about mass?
Warmer.
Warmer than charge.
Maybe not as warm.
Do you feel maybe it's a little easier to understand than charge?
I'm trying to visualize the charge wrapping around the mass boundary. Is that what gives rise to it? Is it electric and magnetic all the way down? I don't know.
Okay. And how about temperature? Where does it fall compared to charge?
Stuff, outer boundary, it has some, maybe an interference.
Okay, but you have no picture really for how all these are connected at all in your head yet. But you're granting that they must, and you're trying to grasp for how they might. Great.
My connection is still very blurry.
What is it? Can you put it to words in any way?
No, not right.
Okay. All right, well, I'm going to pause right here. Remind me if I forget, then to pick back up on my explanation for charge. But I'm going to give it with an explanation of time, space, charge, mass, and temperature. Okay. But first, I want to go more historical to give more credit to, genuinely investigating this thoroughly, the way it's been understood. So in the past, what other forms of charge, before our modern day, before internet, we communicate like that, how did people actually encounter charge? Lightning, great one. We've all kind of experienced that one. Good. So it's a very familiar, shared one. What other sources of electricity do people engage with or physically encounter?
Yeah, getting static.
Static electricity, right? Those sheets, or just walking across the floor and run into somebody, zap. Okay, that's pretty familiar. What else? St. Elmo's fire. You guys ever gone sailing?
No.
Been sailing in a storm when it's raining, and you look at the very top of the mast, and there's this light, and you're like, we don't have a light up there.
No.
That's an actual. I've heard the term. I did not know that. Huh.
What is it called?
Oh, it's St. Elmo's fire.
St. Elmo's.
It's a little lightning spark at the top of the mast. It just keeps there. like
Interesting.
this
The
long.
top of the mass.
You've seen like the globe things on the
Yeah.
inside with that globe. Well, it's like that, but green and blue.
Yeah.
Okay, and it's at the top of the mast. Doesn't matter if you have a wooden mast. Doesn't matter if you have a metal mast. Doesn't matter. Okay, because you're going through a field of charge, right? But all of this point collected right there so much that it just the jump, the gap, spark gap is there.
Yeah.
Okay, there's lots of legends built around that.
I associate charges that it seems sort of mysterious, and then you have these momentary glimpses of interaction.
Yeah. Most of the time, it's really trying to hide itself until it doesn't. That's our experience at kind of scenes, right? What else? Any other forms?
Ball lightning.
Ball lightning. Have you ever seen ball lightning?
I have not personally. I've seen some videos. I've
Uh-huh.
heard it mentioned, and nobody seems to know what's going on. But I may have some ideas.
I've never heard of ball.
You've never heard of ball lightning?
No.
It seems almost like an alien topic at first, but it's a real thing. It's just much more rare than lightning, so the conditions to be right. If you've seen it, you may have seen it like this. You're in your house watching TV, everybody's doing something, and all of a sudden, zzz, through the wall, this ball, this sphere of, and it just moves around, might stop, and then shrink a little bit and grow a little bit and move around, and then a lot of times it'll go towards a plug and go out, and then like lightning hit your house on the outside or something. Or sometimes it'll just keep going, and it'll railroad tracks and go down railroad tracks or follow power lines, right? Yeah. People have video recorded this. Yeah.
Okay.
So ball lightning's another one. It's a far rarer one to encounter. So there's several kinds of ways that humans have engaged with charge, but in most cases, all of those encounters didn't feel connected, right? If you've seen ball lightning, maybe you might have called it something different. First of all, besides the name lightning, you might not have connected it to lightning. Seems like a very different drastic thing. So in general, putting things together that have to do with charge was a big step in the first place, okay? And for us to even ask, wait a second, lightning is composed of something that's different than weight, guys. It's not, you can't talk about it in terms of weight. Whatever that thing is, it's not mass. There's another dimension, call it whatever you want, we'll call it charge, but it's in lightning. It's in ball lightning, it's in St. Elmo's fire, right? It's in, just popped in my head. Have you ever watched the sunset through a telescope? Or have you watched sunsets before? Like when right at the last instant, have you ever seen the little green flare?
No.
Have you?
Kind of like the aurora effect or something like that, or
Well, the atmosphere distorts the colors of the sun, so it stretches the green one to the top. So at the very last instant, if you happen to get a little undulation like this, just enough to peak up, it might be enough to flare from your point of view and see a green. It's a rare thing to see, but if you look through a telescope, you're more likely to see one. Anyway, green flare is a nice, cool one too. It's also made up of charge, right? It wouldn't be natural to connect that, but also photons, light, we found out, are made up of charge. Okay, what do I mean by made up? They definitely are composed of. It's one of its components. So you cannot have the thing we call photon, you cannot have the thing we call lightning without whatever the magic thing is we're calling charge. But it's just, at this point, a dimension. It's at this point a fill-in name for this mysterious thing that we know is different than mass and still real. Different than time and still real. Different than length. Those are all real things, measurable real things, right? And it's a different measurable kind.
Yeah.
The story we need is a story of bases, a story of dimensions. I'm going to mean bases and dimensions mean the same thing, but those words mean literally the same thing as what they mean in math. Things that divide one. So this wraps up into primes, one being the central number related to primes. Every prime is related to one, right? And no other number gets that status. So one's the most important number to primes. If you want to start with a system that doesn't have any magic, if it's self-contained, right? All of its internal parts are doing something against themselves, but at some boundary, that's it. There's no more needed out here to contain everything on the inside. If that's what's going on, then the different actions in the balance And I want you to allow them to be much different sizes each other, but you can rescale it so that they're kind of close. But you should, if you are, allow in your head or color code them so you can keep them track if you're trying to keep in your mind. There's a small twist of a certain size, a bigger one, and there's a bigger one. And there's 5 different sizes of actions, but you can have 44 of the small twists, 35 the next size ones, and 18 and 32 and 8, right, of all of them. But what are all these things doing together? They're breaking up into a number of pieces and strips that are doing different things wrapped into each other over and over, the same things over and over, right? But lots of things are happening inside. What's the outside? What is it? What is it representing? The system. And the system, in every case, is going to be the reference. And the reference is represented by a very, very special number. The 1 is this whole projection, okay? And it's very specifically 1 at the scale of 1 second, 1 meter, 1 coulomb, 1 kilogram, and 1 Kelvin, all at the same time. Yeah. Okay? Those dimensions all agree that this projection at its stabled external scale is 1. Okay. Numerically, logically, coherently, they all will agree to that every time. Even though all of them divide this 1 different ways, making them different dimensions, they literally break up this projection in different size pieces. They divide this 1 in different ways. But there are dimensions that all agree to the 1. Okay, so we start out with the most important number of all of mathematics, 1. There's one other number that's just as important, 0. Yeah, I wouldn't say this is more than it. They're both really important. Because once you have a 1 and a 0, you have a system. You have a scale you've picked. You have a whole thing. We have a geometry who's projectively the 1, and it's being broken up in lots of ways on the inside, and every boundary created by that breaking up process, meaning if you were a fluid point, small anywhere you wanted to be in there, and you wanted to move around, if you couldn't cross a certain boundary because of the fluid action there is like this and this on both sides won't let you do it. If you run into one of those, the boundary in between the two is the 0 of the system. The whole surface in between. It can look like a fractal, it can be a smooth wall, it can be any surface, but that surface is the 0 of the whole projection. And it's a complex, very developed, fractally connected surface. That's the interesting one. That's the boring projection, and they connect via the manifold, the minimum manifold. Okay, so we're connecting the numbers with the geometry from the get-go. The whole system is the whole 1. All the way out to a whole meter, a whole second, okay, a whole kilogram. All the way out that scale, all these things agree at the projection at 1. And as we go in, each of them divide up the 1 in a different way. Now, all the different sizes of rotations define the bases. And we have to give the bases names, but the bases will always be, no matter how many of these systems you throw together on top of each other and their boundaries have to make into a balance, so then you have a connected system, all of them will still agree to the original rules of the first system, because before you connected them, they were that, right? So the base rules and connections, or the bases, will never change, no matter how more complicated you make your chemistry and biology and so on. Time remains the same kind of base. Its expression gets to change as you wrap it up in different ways and make it dense, less and more of it. But it's the same base, meaning it's playing the same role. It lives on the same scale. It divides the domain up in the same way every time. Okay, the only thing you can screw with it is how much of it is there. Is there 44 of them doing it now, or are you making a place where there's 43 that's doing it? Did you pinch one out, right? Those are the things you can convert in the bases. But the bases, if in 44 and 43, would still be domains that agreed with the base of time, that agreed that 1 is this exact number, and 10 to the negative 44, 5.43, all the numbers, times 10 to the negative 44, is the completely opposite bound from the first base's perspective. Yeah. Okay? But only from that base's perspective. You zoom out, and some things are twisted and stripped in different numbers of pieces representing the system at this scale now, and because that always changes at each new coherent scale, you end up at a new whole number of pieces of things representing the system. If it's a different number, then they're going to have a different dynamic too, right? The energy of the system is still contained, but if you go from this scale to time to space scale, different dynamic happening on the space scale, a different action dividing up the domain. So the first thing I really want to develop in your head is an intuition that if you have a projected fluid, it's balancing itself, and it's projecting a boundary where the edge of the projection exists, but there is nothing needed to hold that boundary on the outside. It's doing it all from the inside. It's basically, it's like that's as far as it could reach, right? That's why it's there. No magic, it's just as far as the energy from the inside could actually reach out. To get to charge, I really want you to develop the intuition of what each base is. Try to separate the names historically right now. Forget its charge. Just think of it as dimension 3, base 3. Okay? We started at base 1, which I told you was called time. Just think of it as base 1. It's the small one doing 44 things over and over and over and over and over. Everything above it is standing on it. So it will always be confined by the rules of it. So time holds together all of them. The way the bases fit together is the geometry, right? When you see the picture of how they fit together, the inside's a hyperbolic figure-8 knot, and every point that never makes it to the edge in the hyperbolic figure-8 knot is in the time domain. Let's look at the picture in the book. I break this up in the diagram on the inside with, actually I should draw that. So keep this picture in your head, and I looked in there and said, there's the figure-8 part. I can wrap a circle around it. And then circles of the same size, there would be exactly 6, right? Just the rule of circles, making the next available scale. But then we have a different one. We have a circle that goes from here to here and out here to there, through, right? Remember this picture? So the connection here is we have small circles, the smallest one, which is the smallest base of action, the smallest thing is doing the thing. But then we have this big circle that wraps all the way up and over to that side. Okay? There's another one on this side that's wrapping all the way up over to that side. Or really, you connect these two and you let that thing go around, around, and around. Okay. Yeah, there's a picture of it. All right, so this is what I want you to think. The outside base, the big red circle, it is externally presenting itself like this. It's different than... Okay, you get what I'm saying? It's just 90-degree twist. There's a different representation from the outside, a different way you see this thing spinning. You see a circle spinning about its own axis, or are you seeing a circle go about that, like a rotating coin? Okay.
Now that what you were just describing, that kind of sounds like a torus.
Okay. Why?
Because it's a circle enclosing itself. Because you take a piece of paper, you connect its edges there, and assuming it was pliable, you loop it around, just a circle looping around.
And then the other, yeah, both of them, there's no more edges.
Yeah.
Meaning you could send something, an ant, to walk any direction straight on that path, on that geometry, and it would never fall off the geometry.
Right.
Yeah, it would stay on that bound. Great. So I'm claiming now that if we're outside of this even, then we're going to be in a region that's being broken up by the outside pieces, standing on top of this, which has the inside ones that always stay inside, but this one here that's inside, but it's doing something to the outside that's, it's doing a periodic thing back and forth and back and forth, back and forth, right? It's undulating the shape of the outside back and forth over a cycle. Great. And not in the way that this one's doing it to the inside only. This is a internal only construction, I want to say, and the outside is a half in and half out. Okay, space does half of the binding job of the inside. Its other half of the job is binding the outside. Not the whole outside, but one of the binds of the outside. Which?
But, using the word space, it brings my...
Sorry, the second base.
Second base.
The second base, what it does, it's Mobiusly connected to the inside and the outside. It goes once around in the inside, once in the outside, once in the inside, once in the outside, okay? The inside, when it's doing inside, we call it space. When it's doing it outside, we call it mass.
Okay.
Or you could say it this way. Whatever the shape, the path of closed cycle that we're blaming on base 2, space, okay? If you let that same cycle go around the Mobius construction twice instead of once, it's now a trivial representation of mass. It's a different base, but it's connected and built from the other one.
Yeah.
Now, I think part of the confusion might be here with that is because the way, at least I was introduced to it, you have like, basically the time, which it sounds like you were referring to as base 1, it's listed as balance, 0.
Yeah, you're right. Let me fix that. I'm going to stick with this. Let's start with base 0 through 4.
Okay.
There's 5 of them, but I label them 0 through 4.
Yeah.
Good.
Right.
Yes. Let's do it that way.
Oh.
So from the outside, there's a hole. We don't know why it's there. We see the universe, it's here, but our universe, if we're really godlike and can see its structure, we would look and see, hey, there's a hole to reality. Really small, but if you look real close, there's a hole. Like there's a size you can't get past. We don't know why. There's nothing that direction smaller for some reason. There's a cutoff. Yeah. So if you then ask, what's the shape of the hole? Not just the size, but what does the boundary of it look like? Then it turns out the boundary on the outside of the hole is 4-dimensional.
Okay.
The intersection of a 2-dimensional circle and another much bigger 2-dimensional circle.
The hole has 4 unique characteristics, 4
Yes.
dimensions.
Yeah.
Okay.
Yes. Which ones confine the structure and the shape of the outside over and over and over? The Planck length,
The hole itself is
the one time on the inside, to be anchoring what it does now when it's on the outside. Okay. And then Planck mass, that's the outside. So it's inside and outside expression. Divided now, you would think, oh, well then I should do the Planck time and Planck charge, right? Inside and outside, which is true. Yes, except for the Planck time is the 0th base, and it's the one that's the tetrahedron, which is self-dual. It stays inside itself. It always rotates back into another tetrahedron, which stays another one over and over and over. It doesn't ever go out. Space is going out, in the balance.
Yeah.
Okay, so that means on the out, since this is supposed to be the outside representation, the structure of the outside, instead it's twice around this one. The inside gets twice around from its point of view, and the outside gets twice around from their point of view, and that's the bound. So this is literally our structure in every single one, right? The 4-dimensional structure is set by those. Do you have a picture now in your head what I mean by base? Think a clock. You open up the clock and there's a big gear.
Yeah.
That's one base.
Yeah.
There's a small gear and there's a real tiny gear. There's 3 gears. There's 3 sized gears. The tiny one's going fast. The middle one's going faster or slower, and the big one's going so slow you can't even see how fast it's moving. Right? That's what I mean.
Now, Thad, this sounds familiar to what a lot of great thinkers of the past were saying, that some of their ideas were called crazy at the time. That's funny.
It can't be right unless somebody's calling it crazy first.
I'll say.
Yeah.
I mean, because we're in a world where what the sane apparently people do is ignore that we have a list of 44 constants of nature that no one's explained yet. We all believe that according to our best science, that these things describe reality correctly, more correctly than anyone else's opinion has ever been uttered. Any other sentence has ever been uttered. Somehow there's more truth in those measurements than all the stories we've made up. Why? Because all of our stories can't even predict one of them. They just don't make sense of what we see. And if we trust that measurement is an honest representation of what's going on, then that we should all be like playing with those numbers. But normal is to ignore them entirely.
Yeah.
You know?
Well, it's hard. And sometimes people give up, kind of like when we're doing that little puzzle there. Here's something that's fairly simple. Here's one additional component. The difficulty went up exponentially.
Yes, it can. But if you decide from the beginning that you're just going to do it until it's over, if that's not a question, you just say, I'm going to figure this out. Why? Not because it's an ego trip. It's because you want to get past your ego. Like, understanding this, like, wow, I can't believe how difficult this is. This is beyond what I thought it was. So understanding it transforms me into something I didn't even know I could be yesterday.
Yeah.
Right? That's the point, right? Isn't it life? So those are our bases. 5 bases in a system, and you can kind of imagine in your mind now just changing the sizes of the smallest rotations and changing them and see what it would do to the system. You might imagine that, okay, there's a more complex manifold, but fine, it's still a manifold, a balanced closed system, right? You can start to see that. Well, I want you to practice that because those different universes, those different balanced manifolds you create by changing the different size of the bases that are rotating in them, those literally are models for literal universes, right? I mean, this is the most coherent, logical way to build a universe from the get-go. What are all of its boundary conditions? How do those boundary conditions define all of its properties and potentialities? That's it. That's all there is to do, really. Okay. Okay, where am I going next? Charge. So we have this role. You kind of notice that charge is really important. Well, here it shows up twice. It's really important, okay? In the external construction of the world, it's kind of setting it. Out of the 3 things here, it's the one that gets the most importance, right? Because it shows up twice. Well, now that we have what my story for what all the bases would represent, these different rotations against each other, then I can try to talk about the base charge specifically now. And to do that, we want to go into how the external world geometrically connects. First answer, hyperbolically. So let's make it like a hyperbola. There's the equation for hyperbola, okay? But I don't want the regular hyperbola. I want the closed hyperbola, the self-closed hyperbola. So I want its volume component, its volume element, to be divided over a circle. It just keeps wrapping around the circle over and over and over. Okay, and then this whole construction, for whatever scale ends up working for, has to be applied to some system that has an external domain. It doesn't go to infinity, so it's some number that's not infinity. And within that number, there's going to be 2 orthogonal twists, meaning one twist belongs to one dimension or base, and the other one belongs to a different base. Okay, and how do you represent orthogonal numbers? You can put them to the power, and it's obvious they're orthogonal, right? So I'm going to write it like this. There's our 2 twists, okay, of just 90 degrees. And the Planck mass is the bound that we want to be our external bound in. So this simple equation, the hyperbolic vortex equation, golden equation. Why? Because the solutions, again, you already know, but I might as well go through it again. The solutions give us our jeux. Jeu 1, the picture here really helps. So this is a hyperbolic vortex equation, meaning this characterizes exactly everything we need to know about how, from this boundary inward, the things divide up. And they are partitioned into 6 kinds of things, 6 ways. You get jeu 1, jeu 2, jeu 3, and jeu 4. But jeu 1 is like, it's not 0, so I put it up there. And these represent the partition zeros of our connection. This jeu 3 and jeu 4, roughly picture of them, can also be represented, remember, by jeu R and jeu theta. Those are the 6 that I mean. Or you can write the number for this and you get some other number times I. It's real and imaginary parts. Now the number, the string of digits for jeu 3's real and imaginary parts are the same. The string of digits the same here too, but the sign's opposite. Okay. And then the same number, okay? So there's a lot of symmetries, of course, in the system, but this is just the hyperbolic connection from the Planck mass boundary inward of our domain. Okay, and its partition constants, this one is much, much, much smaller, closer to 0 than any of the rest, right? So if we apply that partitioning to the smallest external bound, or charge, then that's this, jeu 1 to the Planck charge bound. Remember what that one is?
Oh, it's the mass of the electron.
The electron charge.
Charge.
Yes. This is the best way of getting an actual answer what you want. You want to not just know what the dimension or the base of charge is representing, like what action, how fast, where is it fitting together? That's helpful. But you want to know, how the hell does that lead to the electron's charge? That's where charge is showing up in reality, right? So the electron's charge takes just the charge action, the rotation of that scale, base 3 in our model, okay? Base 3 partitioned by the smallest partitioning in our hyperbolic vortex connection happens to equal the electron's charge. It defines the electron's charge. This is a really beautiful and simple equation, okay? And let's remember, J1 squared is also the fine structure constant. A beautiful and simple equation, but it's just a partition structure we're talking about. And look, the fine structure it has two things in content. The partition constant that it's containing and that it's squarely bound.
Yeah.
What does that tell you? There's a system that's using the charge boundary under square arrangement. I just erased it, but charge squared, right? You see the connection here? This structure, the fact that this is a constant of nature, tells you that not only do we have J1 as a thing in our system, but the way it's held in our system is intersected exactly with another one. There's a 90-degree intersection there.
Yeah.
Okay? Great details, right? We pieced together something that's going on. All right, so charge is now one of the bases explained in action from the other bases below it, but it's the base that defines the electron charge by being the smallest hyperbolic partitioning of just the third base, the thing we're calling charge. Okay? So not only do we have the boundaries called the Planck constants, in this case the Planck charge, but we have to fit them together under some geometric structure. And this is the one geometric structure that fits all the external boundaries together, which I think that's mind-blowing alone. But I want to continue down what else comes from just this pattern. When we put these j's together, and what are the j's again? They represent our partition constants of this connection, literally of this connection. You just think of it algebraically.
Yeah.
So you write this out and solve for x. J's are our solutions for x. They're the numbers that solve this pattern, okay? And they're the only ones. So when you put them together, what do you expect? If you add them all together, think of them like vectors. Add J1, J2, J3, and J4. Make arrows from this inside out, and then take all the arrows tip to tail, where will you end up? No, zero. Back in the center.
Oh, okay.
Yeah, if you add them up. Yeah. Yeah, so if we just take all these constants and add them together, this is really beautiful, I think. If you pay attention to the algebraic symmetry, this is what's happening here. We start out with something whose base partitions are defining just the balance of zero, okay? And then when we take the product, so we don't want their sum now, we want their product. What do they produce?
A circle.
Yeah, 2 pi. And what is their quadrants, which is the square of each added together.
Negative 4 pi.
Yeah, isn't that really, really, really beautiful? Now remember, we started again, we have a modern day explanation that what we're in, the shape of the universe, as far as we can tell, is this Riemannian sphere, which is what? Well, it's a sphere connected on the boundary to another sphere. All points are connected somehow. Okay, and then we need a picture somehow, which we don't yet have, but that's the story we're currently living in. Here, we ended up with what?
Some of the simplest, most
By the way,
geometry.
if I take minus this one squared, if I take minus all of it, then we end up with positive 4 pi. And both the minus one and the positive one are what we call quadrants, which tells you we're getting a division system here that combines to make a sphere, and combines to make the completely opposite sphere, and combines to make a sphere. Its Mobius connection goes circular bound spherical projection. Okay, what else? Let me see the equation I had on the bottom there. Is it on the same page for the quaternion stuff?
Internal logic.
Maybe. Yeah, good. All right, so this algebraic equation, I'm going to put it up on the board and you guys come work it out. Just factor it because I want you to be able to say you've done it. AD plus BC squared equals, and all you need to do is factor it so that you can prove that the left-hand side is actually, in fact, equal to the right-hand side. Because this equation itself represents the structure of quaternion logic. If you have a structure who has 4 bases, A, B, and C, D, and they are maintaining this equation, then that 4-dimensional system is quaternion. Now, there are several ways to write a true quaternion logic, several varieties of how to swap them up. All of them are true. If you have a system that satisfies one of them, it's a quaternion bound system. So first step for you guys, come here and factor both sides to verify for me that you know that that's true.
Okay.
Oh, right. I see. Yeah, so the
Doesn't even slow down. Looks pretty good. Yeah? How close are you?
last one.
Okay, good. So with this,
I agree. Equation's true.
you got it? Okay. So with this structure, I wrote down a few of its symmetries. I'm going to write down a couple other ones that we're going to use in the next part of the conversation. From the picture, if you remember the symmetry of the picture, it would be obvious, but I'm going to write this down anyway because we're going to use it. Where to go? Imaginary part of G3 is equal to the negative imaginary part of G4. They're opposites. The real part of G3 is equal to the same as the real part of G4. Okay. Another one is that real part of G3 squared plus the imaginary part of the same one is equal to Gr squared. Maybe that's enough. We'll see as we go. If we need any more, we'll get them from this. All right, so now we verified that this is a true quadratic equation, right? Which you might not found all that impressive, except for having a system that maintains itself this way is literally the definition of being a quaternion system. It's a closed division algebra, right? It has multiplication, division, addition, subtraction, powers, inverse powers, all the mathematical operations are naturally built into it. So we really love it. All right, so let's check something here. If we set A, I know you guys have heard me say this, let's do it. If we set A equal to the real part of G3, and we set B equal to the imaginary part of G3, and we set C equal to the real part of G4, and D equal to the imaginary part of G4, let's plug them in and see if it's still true or if we've broken our form. We've already proven it's a quadratic form. Now we want to see, does our system obey it? Okay? All right. I'm going to erase this now because I need the space, but this is part of our conversation still. This is what we're in. So we're just going to write it longer and put all these things in. Sorry that we have to write real and imaginary. It's just, I like to be clear. It makes it more bulky, but fine. So we're doing the real part of G3 times by the real part of G4 minus the imaginary part of G3 times by the imaginary part of G4 Let me know if I make any mistakes here. And that's now all squared. We'll do them in pieces this way, I guess. I'm going to do this one now, plus AD, which is the real part of je3, times the imaginary part of je4, plus BC, imaginary je3, real je4. Okay, and that one's squared. So let's work out just both those two before we move on to the right-hand side of the equation. Since the real part of 3 and the real part of je4 are the same, let's turn all the 4's into 3's. Let's turn, in every way we can, all 4's into 3's to reduce number of variables. Being able to erase it actually is nice. So here I can just swap. Since they're equal, I can literally just swap a je4 here for a je3, right? And in the real case, because real is equal, but in the imaginary, here's another 4 that I can put into a 3. And the other, that one's already a 3. Okay, so the reals are done, but now when I want to swap imaginary 4 for imaginary 3, I have to make it negative. So let's try that. With imaginary 4 right here, let's make it a 3, but now we have to put a plus there. And imaginary 4 right here, put a 3 here, and now we have to put a minus there. Okay. Cool, so we end up with real je3 squared plus imaginary je3 squared, which here from this equation is equal to jr squared. All of that squared turns into jr squared squared, so that's just jr to the 4th. Okay, that's this whole line right here, which was just this piece here. Agreed? So far?
Still absorbing.
Okay. Well, this piece right here we've done, turned it into this, and this turned into that. Now we're going to do this piece, which is this. Okay? And so here we have imaginary 3, real 3, imaginary 3, real 3, but minus. So this thing goes to 0 on the inside and squared. So it's plus 0. Okay? Now we're going to do the right-hand side of the equation. This whole left-hand side is now just jr to the 4th. That really got simple. So we're saying jr to the 4th equals this side if we put in a, b, c, d. Okay, that's what we're claiming now. So let's do it. A squared, real je3 squared plus b, imaginary je3 squared times c, real je4 squared plus d, imaginary, plus imaginary je4 squared. Cool. Well, this equation again comes into play right here. Turns into jr squared. Cool. This one here, let's turn into, because they didn't write down the 1 for 4's, let's turn it into 3's. If you have a je3, or sorry, the real, it's exactly the same, so I can just swap it out. Nothing, don't have to change anything else. So turn the 4 into a 3. The imaginary, I have to swap it out. If the 4 goes to a 3, I need to change a negative sign, but the negative sign squared goes away. So here, in this case, I can just swap it out. Agreed?
Yep.
Okay. And now it's the same as that. jr squared. And this time they're multiplied, not added. So jr to the 4th. These 4 pieces of the way our picture is being divided, our domain is being divided, these 4 pieces inherently, intrinsically, automatically obey, if not define, the quaternion connection. Now, here's the next really amazing point. And they do it supersymmetrically. Not only is this construction defining jr to the 4th radial connection of our connection, that is that. Not only is it that, it meets this condition if we started from a different set. There's 4 different sets. You could swap out 4 and 3, swap these now, right? And you could swap out the real and imaginary ordering, and it still works perfectly. And it also still defines r to the fourth. So there's 4 ways, supersymmetrically, that these operators, these parameters, bind under a quaternion construction. Okay, I think that is mind-blowing. Because if you only follow the algebra, it's beautiful. Right? If you hadn't connected to what it means but to the geometry, we're balancing a 4-dimensional geometry under the quaternion connection, meaning its bases themselves balance like that all the time. Yeah.
Can you just go real quick, because J3 and J4 can be expressed in terms of radius and angle. I think you already did that, but I was still, my
Do it
brain
again.
was still
Good.
catching up a little bit.
Okay.
Because I feel like that's the step that my mind kind of glossed over a little bit.
Okay. Remember what they are. If we graph them, J1 is right here, roughly. J2 is right here. J3 is somewhere up here. J4 is symmetrically on the other side down here. Okay. Please excuse if I make them symmetrically in your head if I don't. Okay, and this arrow. So J3 has a real and an imaginary part. What are those parts? This is the real part of J3, right here. This is the imaginary part of J3, here. And this is Jr. It's a triangle, okay? And it's at 90 degrees. And that's their relationship, the Pythagorean relationship, okay, built in. Great, so that's their connection. Or you could also talk about Jr as the angle, J theta, J theta as the angle from the origin to that radius direction.
Yeah.
Okay, that radial direction. Great. So those are all, they're just 2 different ways. The r and theta are just 2 different ways to describe getting there.
Yeah.
Yeah. You can do it in a circular way or you can do it in square ways. Good. All right. So I think where we're at then is we have a 5-based system that's only hyperbolic. Actually, let's move over to the board. I'm gonna carry you through the board now, or the poster. Yeah. Story really is just the minimal arena under 5 hyperbolic balances. You see what I mean by hyperbolic, I hope, right? It's literally hyperbolic divisions that define them. And I mean, that's a constant that we talked about before that's hyperbolic, gamma function related. Okay, so those are the claims that this one system, the one, his external reference, is partitioning into this many pieces at this boundary like this, hyperbolically that way, this many pieces in this way, this many pieces in this way, and so on as we go. And at the bottom, we get to a system that's number of pieces define the whole derangements of the system of the 5, which is really beautiful, making it a whole derangement system because we close out. We get full derangement at the bottom, we get closure at the top, okay? These equations alone give us values for these rotations, which give us the ability to predict the numbers of whatever digits we want. I've listed to 15 because I care about to 14, okay? And the derangement numbers here are written right here with the rotations, okay? So the 5 rotations starting from 0 to 4, and the 5 derangements that are associated to those 5 rotations starting from 0 to 4. The connection between them, the bottom one for the base 0 is all derangements of the 5-base system, okay? It defines all 5, all derangements. The next system up is defined on the break and scale symmetry between the first one and the next one. So our multiplication by 7. So we get a different factorization that's now doing a different thing, but 35 times, not 44 anymore. And then externally, we have 3 things that are hyperbolically, literally this hyperbolic connection, which has a +1, 0, and -1 for our k, okay, to define the 3 different sheets. The +1 is this surface, the colored surface you see here. The 0 is the grid right outside this one or also inside this one. You can see it's duplicated. And the -1 is the sheet down here and the sheet up here, the surfaces, okay? Those are the hyperbolic surfaces of hyperbolic geometry that define the external connection here. And this 0, -1, and +1 are literally the 0, -1, and +1 I'm talking about.
Could you explain the 0 again?
0 is the cage. the bounding surface
Okay.
between them. So
Yeah.
take this one
Yeah.
and put it on top of that one, so it surrounds it. That's what I really mean.
Okay.
And in between the two of them is this bound. But none of the surfaces get to the bound. They're divided by it. Right? So if you're an ant on the surface in here, you would never be able to make it to this actual cage. You get real close all the time, but you're never really touching the cage. If you're on this one, you're never touching the cage. You're always missing out on the outside. So both of them are separated by the same cage.
I see.
That's what, okay, good. Good, now you're seeing more in the thing than before. That's great. These 5 equations are graphed here. Bottom one is this one's that one, this one's that one, right? Okay, so this is what they look like at this specific scale and so on. But let's dive into pictorially. At the bottom, we're saying we're getting the whole figure 8-ness happening. Okay, wait, that kind of looks somewhat reasonable already. I'm starting to see some figure 8-ness in here. But now I want to drive a connection between them. Imagine taking a knife and slicing this figure 8, the one that's coming up this way, and pushing it down. Inverting just that one, leaving this one the same, and inverting just that one. That's all you do. What does it look like then?
Like that.
No, slice it this way and push just this one all the way down. Or that one. Push one of them all the way down. Ah, okay. Suddenly these things look somewhat connected. This one's asymmetric. One size does something, this other one does something completely different, right? So connection between them, okay. By the way, charge boundary. Yeah, mass boundary. Space, which is logarithmically connected, this logarithmic thing, and time. This is our whole story of what the domain is. It's just these 5 dimensions. Now we're interested in characterizing all the unique intersections created by those 5 dimensions. Okay, so there's the 5 boundaries of those 5 dimensions right here. The Planck constants, literally determined just from the rotations and the derangements, and every case the same way. That's kind of nice. Okay, now the connection down here gives us our jeux. We just had that whole conversation. These are all the algebraic or geometric algebraic transcriptors for the connection in our geometry. Okay, all these things are true statements that maintain the rules that we're interested in. All the way down to the quaternion form itself, defined by J R to the 4th, held supersymmetrically in 4 different ways. Meaning if you start with this prescription, A is the real part of J3, and C is the real part of J4, and B is the imaginary part of J3, and D is the imaginary part of J4, and so on. You put these numbers in for these bases, and you get this in each of these cases, giving us the quaternion algebra from our geometry, from the way our geometry is connected. This is beautiful, right? And you could sum up some of these or rewrite this sentence, this product of these 4, like this. There's another way of writing it. Product of all the jeux is 2 pi. The sum of all the jeux is 0. The sum of all the jeux squared is negative 4 pi. Just another weird way of writing this. Why is that important? There's a lot of products and sums that we're going to be interested in, and if you don't ever learn to see it this way, then we have to write forever. It's too much writing. So this is useful to see this, but it's just the same thing as this. All right. But then also you might notice this. There's a relationship between the cubic product of these and the square sum of these. The squared argument sum of these, just multiplied by pi over 2. Beautiful. I mean, I really think this is in the category of e to the pi I is -1. These numbers don't just give us a connection between a few things, they give us the whole algebraic geometric connection of all things. And to get to the all thing part, I mean it literally. That structure is responsible for how every constant of nature has its property.
These really work out to be the same.
Yeah. Beautiful, isn't it? Our reality has that structure in it. It really is.
It's just like,
Okay,
whoa.
so now we're moving on to the constants of nature. Okay, and then this is the mass. Well, in the red, orange, and this section is mass boundary conversation. And then there's the legend and stuff. Constants of nature. It's really fast conversation, honestly, because it's just this prescription, just in the yellow. Everyone here follow this prescription. You have a primary action and a primary set of boundaries determined by the dimensions of the measurement.
Yeah.
The terminal action and terminal set of boundaries, which aren't, these ones are unique for each constant of nature, but every constant of nature shares the same internal where they flip over. So they're all closing over on this one fixed set. Okay, so you get to solve for the terminal action, but you don't have to solve for the terminal boundaries. It's always the same. So you apply this prescription to the measured number for every constant of nature, and you check against every one of these j's because we know these are the partition parameters of the thing that's holding it together. So you check what's the geometric equation against every one of those, and you find, well, here, this one's in the real direction of j3. It's making a circle.
Yeah.
Interesting. You see how simple that is to read now? And down here, we have an invert, 1 over a circle. But this is now instead of the j3 direction, the real part of the j3 direction, it's in j4, the whole connection. 1 over 2 pi, 4 pi, 1 over 4 pi, 4 pi, 4 pi, 8 pi, 1 over 8 pi. That collection alone is worth really absorbing. Now, gravity has some natural connection to this. Some inversion here, right? We wouldn't have known that before. First of all these, you can say, hey, I see a connection between these now. I see a connection between these. I see a connection between these, and so on, right? You can connect them either by their 2 pi-ness or by their what part of the partitioning they're in.
Yeah.
Great. Great. And now we keep going down. The ones that aren't just pi's. Remember, the system is a system that's Mobiusly connected. The boundaries on the inside are what's projecting the outside shape, but they fit together such that they have to wrap around once, and they act like a certain thing when they do, and they wrap around twice, and they get back to how they were before they wrapped around once. Okay? So there's a Mobius construction. Okay, now this one, these two are both on the right-hand side, 1/2 times the real part of the infinite power tower of I. What picture comes in mind when you think of that? What could that possibly mean? Times by r squared. R squared is great. We have our radius. We know what it means. We have it squarely intersected. Cool. So we have a system of what size? We know exactly the size.
Yeah.
And now we're saying that it's splitting half of the real part. Half of the real part, the infinite power tower of I, is belonging in that direction. The other half is splitting in this one. Okay?
That's the
Great, great, great. But what else? What does this mean, you guys? What's infinite power tower of I supposed to mean? 1 I means a rotation.
It's going on forever.
If you put another I, but it's to the power of, that's a rotation that's orthogonal to the first one.
Right.
Now, if you put another one, that means you've added another rotation that's orthogonal again. What if you just put a system that's rotating forever, but it's spiraling in? That's this guy.
But with infinitely many orthogonal directions.
Yeah, not the same way as before. And then do that over and over and over and over, and you're zooming in. It's a well, if you look at the eye to eye to eye, 3 Blue 1 Brown has a great video, I think, on this. I think he's the one who did it. Shows you the spiral that goes in as you get higher and higher with more and more eyes. Go into this point.
Oh,
Yeah. This is the x coordinate of that point. That's setting how these boundaries connect. This is getting really beautiful, right? But now let's go down. The hyperbolic sine squared of the hyperbolic fixed point of the cotangent, the one that's already in hyperbolic geometry, you can't take it out, right? So the fixed point of hyperbolic geometry squarely balancing here with these guys. Wait. We're showing that the same connection is hyperbolically bound and divided by internal infinite sequence of rotations. Next one, on the right-hand side is zeta prime of 0. The first derivative of the zeta function at 0 is applied to j theta squared. Okay, what are we trying to say here? We're saying that these bounds on this constant, these bounds are maintained defining the first derivative of the zeta function at 0. Okay, and what are we doing? We're just squarely rotating in our theta direction. The next constant, which, by the way, this one was j1 squared, or the fine structure constant, divided by 2 pi. And this one over here is just 2 pi, so inverted without the j1 squared. But here we inverted also, but gained it 2 times. Okay, and we've doubled our power here. Very interesting. Let's keep going. We got another zeta function. Zeta of, this is a 5, remember? Yeah. So all 5 things are five hyperbolic partitioning things in the zeta function, the way it partitions, in this direction. And here, square root of the zeta of 2. Instead of all 5, now we break them up, 2 and 3. See, this is really cool. We start up j theta But now we go to j theta squared, and in two different directions now, we take our 5, we take 2 and go that one way, and 3 go another way. And what ways? There's the bounds. Those are the ways. This one gets constructed under the square root of zeta 2 bound, times by that and squared. But this one is inverted in a sense. The Planck length squared Planck mass, Planck length squared Planck mass. Planck time, Planck mass, Planck charge squared. So we're swapping out the mass of the electron for the charge of the electron. This one with this one together becomes E squared.
Yeah.
Okay, we're just swapping the mass electron for the charge and the pi, and we're inverted. But then we got 2 and 3. So there's a 2-part and 3-part connection. Mass gets 2, charge gets 3. And we keep going. The magnetic constant, mu b, we get zeta of 3 times the direction of the r. Mu n, same thing. Okay, and what does it change here? It's the same coefficient at the front, but Planck length squared, Planck charge, Planck mass, all the same, Planck time the same. All we did is we swapped out the mass of the electron for the mass of the proton, and we still get the same construction. The speed of light. We take the zeta 3 from both of these and put them together, get zeta 3 squared in the direction of j3 real. Okay? For Planck's constant, we swap. We give the power square here, and this one's 1. So j3 1 real squared. But now for C1L, the constant out front is 1 over zeta 3. You can just see them. I don't need to read them all out, but I really want you to focus on them. The front pattern is gorgeous and beautiful. It's only made up these simple parameters. Great. Everything in parentheses just from the dimensions. Great. It's actually the most complicated part, but it's really easy to understand. Visually, it's the complicated part, right? The Euler-Mascheroni constant divided by 2 in this direction squared, the same one in this constant. Isn't that beautiful? And these are, again, constants that swap. LP squared MP, LP squared MP, TP QP, TP QP. The same dimensions, just upside down. Even the coefficient up here is upside down. Great. Here, e to the pi. What does that mean? Have you seen that before? I think you've seen that before. What was it referencing when you saw it? E to the pi I is -1. Good. I'll look at this one over here real quick. This e to the pi is what I want you to see when you see e to the pi. It's the infinite sum of pi to the power of something plus or divided by gamma to the power above that. Infinite sum of rotations and gamma divisions. The whole set, the whole collection at once is equal to e to the pi. Okay, keep going. Log of 2 times pi. This has got another name called b sub 2 of 2, and it's defining the electrostatic potential of the electron.
Yeah.
Literally the grid spacing that is put into place because of the electron's field. Oh, and this electrostatic potential constant happens to be the thing that describes the back end of what? The radius of the electron. Keep going down. This L2 is the second Lenscape constant. And this pops up in another constant too. The other radius of the electron, the Bohr radius. Why does the electron have 2 radii?
It's very interesting.
Because it's a
Double cover.
Yeah, because it's a Mobius connection. It has 1 time around and 2 times around. You have to specify both to get the whole system. Yeah.
Fantastic.
Okay. Right, universal parabolic constant divided by 2 squared times by J1 to the -2. So 1 over J1 squared. Okay. But now down here, it's 2 times by pup instead of divide by squared times by J2 squared. Wow. There's another place where pup shows, right here. Another place where pup's up in the front, and it's 2 pup squared again, but not instead of J2 squared, it's Jr to the 4th, our whole structure down there. And the domino tiling constant is equal to the Catalan constant divided by pi. And the Catalan constant you get from, if we take the Clausian function here, we can put in pi over 3, and we get the Giesecke manifold. If we put in pi over 2, we get the Catalan constant. They're directly connected. They're part of the system the whole time. And these, domino tiling constant and the Catalan constant and the dimmer constant, these are the things that are telling us how we're twist fold allowed in our domino connected system, meaning 1-part, 2-part system that you can't separate, or better word is Mobius connection. Okay. Beautiful. These are the constants it's all made up of. These are the algebraic ways of thinking of them that I think are most useful. I, -1 1/2, imaginary golden ratio, -1 1/3. You can see that they're directly related. But the imaginary golden ratio is the base of the equation that we have for the hyperbolic figure 8 knot. It's only made up of a dilogarithm of 1 over the imaginary golden ratio minus the dilogarithm of the golden ratio, or the imaginary golden ratio. It's the argument that makes the hyperbolic figure 8 knot. I didn't know that was the imaginary golden ratio, so I'd before written it just like this.
I don't even think that's in Wolfram Alpha.
It's not.
Okay.
Wolfram Alpha doesn't have
no,
imaginary golden
it
ratio
gives
yet.
something. Wow.
Yeah, I mean,
Okay.
Wolfram Alpha, you can write it this way, but it doesn't know that that's a thing. And it really should, because this isn't the only way to write it. The imaginary golden ratio has several interesting ways to write it. It has an interesting continued fraction. It has lots of rules that are obeyed, just like the golden ratio was obeyed in the gamma function. The imaginary golden ratio obeys the same inverse symmetries. Okay, so a lot of places they carry a role in the same systems. That's great. This side over here, this omega-1 and omega-2 are the internal periodic frequencies of the gamma function. Okay, one of them is multiplied by our internal argument, imaginary golden ratio, and one of them is not. That's the only difference. So we notice in the gamma function there's going to be something cubed with an argument 1/3, and there's a bunch of geometric constants that show up with this gamma of 1/2 and gamma of 1/2 squared all squared. Usually together, sometimes just this piece by itself, sometimes, and by the way, gamma of 1/2 is equal to the square root of pi. Okay, beautiful symmetries, connections everywhere, but then just we're going to be able to read what's on the poster here. Now we get into the mass boundary. This part, mass boundary, balances. This is the most external partition boundary of our whole domain, 5-part domain. Okay, it balances, it splits, and it joins. It's under action, but it always has a balance. And that balance defines the electron mass. And it always has a way the balance at 90 degrees is tearing itself apart all the time. Right? In one way it balances, in an orthogonal way it splits, in an orthogonal way it comes together. So we have 3 orthogonal expressions of the same mass boundary. Yeah. The one and only mass boundary, mind you. It's the same Planck mass boundary. Why? Right there. Planck mass to the 4th power times by, you can rewrite this, by the way, 4 Giesecke constants. 4 times GGI, Planck mass to the 4th, meaning each Giesecke constant gets a Planck mass boundary, as it's what it is, right? But there's 4 of them out there, and there's 2 on the inside. Here, at the mass balance, it's just 4 Giesecke manifolds, literally, okay? And being held together, what? By the hyperbolic falling apart of everything below divided by the break and scale symmetry of how it's expressed, of how space lets it be expressed. Okay, that's it. If you follow that, that should be a picture in your head at some point now. Okay, maybe it's, hopefully it's getting clearer and clearer. So we describe the balance line only using the Giesecke constant and hyperbolic structure of what? Of our 5-dimensional system that's deranging. Great. That's the limit of all the hyperbolic parts. Everything's closed there. That's our balance, and it's the simplest geometry that can be balanced. Splitting boundary and the joining boundary are supposed to be orthogonal expressions of both of these. We have a lot of significant digits for the mass of the proton and the mass of the neutron. We know them really well. And we need to know about 14 for me to say I have a story. All of these claims are accurate out of 14 significant digits. Okay, all of them. Great. So splitting, joining, we split using the alpha-Feigenbaum constant. I know you've heard of it before, but it's what? The number in math or logic that characterizes bifurcations.
Oh yeah.
In any balanced or Fibonacci-like sequence or system, bifurcation over and over and over and over is going to be characterized by that number. Yeah. Okay. The mu plus 3 plus pi. Mu is the number that defines the other 0 of our logarithmic connection. We have a logarithmic connection, right? We have a specific kind of logarithmic connection, a 2-dimensional logarithmic connection, okay? But if you're reaching out in one of the logarithmic directions, then that means there's 2 zeros binding it, always holding it. The 0, 0, the trivial 0, and the non-trivial 0 called mu. So I could change this equation and put a 0 in there, 0 plus mu plus 3 plus pi. And then I'm saying I have both of our logarithmic zeros. I have a 3, which represents a hyperbola that's not divided by 2 pi. And pi represents what? A rotation, right? So here we're dilogarithmic, or you can use it kind of in a vague way to represent a circle. Here we're connecting dilogarithmically, hyperbolic dilogarithmically, a hyperbola and a circle. That's all we're saying. We're connecting, meaning plus and plus.
Yeah.
So we're splitting here, right? And here we're connecting. And we're connecting what? Just the geometric pieces themselves. Now, where do the 2/3 and 1/3 come from? It's really important. The way I wrote this before was -1 to the 1/3. It's also true, right? That would be right here. This would be -1 to the -1/3. That's 1 over this one, right? What does that mean? Our structure is dividing itself in 1/3 and 2/3 pieces. That's just what it's doing. It's a 1/3, 2/3 division system. And so that 1/3, 2/3 is asymmetric, folding on itself. That's where the asymmetry comes from. Literally from the base of the 1/3 and 2/3 because of our imaginary golden ratio. Great. With this 1/3, 2/3 division is showing up right here again. The 1/3, 2/3 splits are how things being torn apart and how they're being put together. Okay? Moving down here, we want to extend. There's no extension of the balance map. It's closed. It's self-closed. It's perfect done. But the splitting and joining, so think of that. You go around a loop in the middle on the waist and you keep doing that loop, you're balanced. But you have other parts that are coming out and then coming back together in some plane, always doing that. Okay? Those parts are also intersecting. There's going to be stuff in between that's getting echoes of what's going on. And the number of intersections, each echo has to be coded too. So I'm going to say that like I want to extend the splitting map and the joining map to also then code all the echoes, the smaller pieces of the intersections. We got the best 3, great. The most important, the ones that manifest what we see. But I want to understand the whole inner gear work. So we have to extend that. Now, how can we possibly extend it? Well, first step, we know how many particles we have, how many mass pieces fundamentally we need to make sense of. There's a total of 18. One of them is the Planck mass boundary, so there's a total of 17 others. Okay, so 17 expressions of the Planck mass boundary will show up. Here's the Planck mass boundary already in our system. So now we have 17 other things that characterize us. That one, and then when we get to splitting, that one, and we get to joining, that one, and now we keep going down to find them. This picture right here is the same thing. I just copied it and put it here. And this one right here is the same thing. Okay, so move them down, and now we're going to try to extend the pattern to look for how the rest of them connect symmetrically. Great, let's start over on this side. First thing, modular forms. Have you ever heard that phrase before? Modular arithmetic.
Don't know what it
Well, in modular arithmetic, you care about just the remainder of the system. So if it's base 5, then 7 mod 5, your base is now the 5, the mod thing. Then 7's only 2 more than 5, so it's equal to 2.
Yeah.
You only care about the leftover of multiples of 5, no matter how many moles. If you say A minus B mod C, you are claiming that A minus B is divisible by C. Clear? It is clear?
Yeah.
Okay. So now let's say it like this. A minus B divisible by C in each case. I'm writing a modular form structure here. And we're picking why these 3? Well, this one we've had given. This is our joining map, and we want to extend it to the others. And you can try all possible combinations of the other available ones to see if you can find a pattern. But you can also try to symmetrically group them up based on what we already know about their properties. Okay, they're listed in families and generations and so on. That's what I'm doing. Families, generations, mapping. You might also notice now what happened in the 1/3 became a direction and 2/3 became a direction. Power operated in this case 2. I'm guessing again at the bottom. Do you see what I'm saying here? We're splitting in 1/3 and 2/3 actions above, but now we're extending the piece. And when we do the extension, we have to actually use the 1/3 and 2/3 connections to do the extensions. They define 2 of the possible directions in the extension, which is really cool. Higgs should be compared to neutron or down or charm, or C or T, right? One in the same position of the modular form. So here, Higgs and neutron, great. Higgs and neutron have a relationship, and the definition here, if this is right, that gives us the ability to now predict all the digits for the Higgs. See where I'm going? And with this equation now, I have a Higgs exact value that can go here, and now if I already had those 2, I can continue the rest of this. So you need to use the masses themselves, these are dimensionless quantities, right, to find relationships you think would be real. But the ones I found, like this, This is really, really, really helpful. 4 over the Laplace limit times just theta to the fourth. The Laplace limit is connected directly to this guy. In fact, 1 over the hyperbolic sine, not squared, of this fixed point is the Laplace limit. 1 over this without the square. So this is the Laplace limit squared.
Okay.
This is the Laplace limit to the negative 2 power. There. This one right here is the Laplace limit to the negative 2 power.
Yeah.
Times by r squared. These are the relationships that this is relying on. So if you change anything here, this would change if you want to try to go through it. But there, that's where I'm at. Anyway, here we go. Hyperbolic figure 8 knot, some basic equation. I think we should really pull this one out. If you look at just this piece, one of these dialogic pieces, it's equal to 2 pieces, a real and imaginary part. The imaginary part is the Giesecke constant. The real part is 4 pi divided by 5 hyperbolic divisions squared. A sphere, hyperbolically divided 5 ways squarely, is the real part. Okay, of just this. Now, when you put both of these together, these pieces show up twice and disappear. And you just get 2 of those with I twice, and then it goes away, and it's just Giesecke twice, and it's BFE, right? But you need to see what it's hiding. Both of these pieces are in there. So the external shape is this, the internal shape is that, right from the get-go. Now, this is going to be a bit mind-blowing. If you write this equation down, and you stare at it and say, wait a minute, how many parts are in this equation? We have an I outside of it all. We have one dilogarithmic piece and another dilogarithmic piece, and both of these have signs. This is plus and this is minus. And we have an argument and an argument, and these are both positive. So an argument could be here. This is positive right now, right? So we have one plus sign. Let's put all the invisible plus signs in so we know how many signs there are here. 1 plus, 2 plus, 3 plus, 1 minus, so that's 4 of them, and another plus. 5 arguments. Wait a second. I just told you that 5 or 2 to the 5 is 32. And arguments have 2 options, plus and minus. So there's 32 ways you can rewrite this same equation just by changing pluses and minuses. Where am I going with this? Why did I say that?
It's almost like there's 5 balance points or something going on.
There's 5 balance points, but if there's 32 ways to write the same thing, what 32 ways will those be? The 32 expressions of temperature. Those will be the 32 full expressions of the external domain. You don't have to guess how we're going to characterize them. You can characterize all 32 expressions, all 32 geometric pieces of the external domain by just flipping the signs back and forth in the 32 ways you can write that equation.
Yeah.
I'm not kidding. That gives you the whole set of chemistry.
Yeah.
That gives you the whole set of boundaries you're supposed to divide into 18 and 8 and 32 pieces. And that's it. That's as simple as you can get. We have this equation, which I think is beautiful and short, and dependent on an argument of a number that I think itself is just beautiful. Okay? And then if you take the same equation and you don't change anything but its signs, try every iteration of positive and negative allowed. That's 32 of them. Write them all down, see what they all equal. They're all a real and an imaginary part. Sometimes the imaginary part 0, sometimes the real part 0, but most of the times they both have non-zero real and imaginary parts. Okay? And each part is a geometric piece of the whole puzzle. It's what the outer domain looks like that we call the n hypersphere of maximal volume, or the shape of the reality that we're minimally in. Yeah. If you minimize it down to the simplest form, then that would be the shape.
Fantastic. Quick question.
Yeah.
Now, if I know like Large Hadron Collider is supposed to be coming back, if we could get some better measurements of the Higgs,
then we become more confident with whether this is right.
Right.
Yeah. Yep. Exactly. Every time we get a better measurement, if it's not lining up with what we already said, then we just immediately say, okay, fine, we're trusting the number. Well, let's update. That would be the fastest way to update if we do have something wrong. What we can do right now is, at least individually, is try to take the actual existing data with its own error bars, which gives you a way to really test your answer. You get 5 answers that can get you close, and then you check each answer against the allowed error bars of the actual measurement and say, well, that's a sigma 18, it's definitely scratched out, and that one's a sigma 2. Well, let's keep it around, it's possible. This one's a sigma 0.5. Ooh, I think that one's most likely. That's what I did. Yeah, and I think that system is logical enough that we can actually code it. So we want to code in Wolfram Alpha this process. We want to say, All right, well, from alpha, we're going to feed in the digits for this constant of nature, and we're going to have you search for the first 10 significant digits, search for what geometric thing could get you there after putting in these boundaries, right? And then down at 9 and 8 and 7, 6 and 5 and 4 digits, probably cut off at 4, maybe 3, depends where you want to code it. But checking those whole ranges for what algebraic thing could get you there. And then divide out 0, 1 and 0, 1 squared and 0, 1 cubed and 0, 1 quarter. On the back end side, same thing. Once we get the answer, then we say, all right, well, from alpha, oh, what do we do when they ask when we ask a question, we pick how many digits, it spits out answers. We then scrub the answers. We code it, just copy these answers and put them in a list. Now ask again with one less digit. Scrub them, put them in a list. We build up our list. Most of the list we want to throw away, but we want to have a reason to decide between them. Our reason is going to be what? Complexity. And then, of course, the answers that spit out, you have to test against the actual measurements.
Yeah.
Let's now build a sequence where we take all the even numbers and divide them by all the odd numbers. Okay, so 1 under 2, 3 under 4, 5 under 6, and keep going to infinity. But we're going to multiply each one. So each one's slightly bigger than 1. It gets closer and closer to 1 as we go this way, but still they're all bigger than 1. So you multiply it by something that gets bigger and bigger and bigger every time. So this actually goes to infinity. It's kind of obvious, right? It sails off to infinity. But if you just shift the sequence so that we get rid of 1 and take all the odds and shift them over 1, so now that the denominator is slightly bigger than the numerator, now obviously it sails off to 0. Okay, cool, but so what? The next step's the so what. What happens if we say, what if we take this thing, this product of infinite fractions that sails off to infinity, and we combine it with the one that sails off to 0? This one and this one together, and now this one and this one together, and so on, and it goes to pi over 2. Do you see in a mystery here? We have something that, okay, I can understand totally why this is going to eventually go off to infinity. It has to always get bigger and bigger and bigger, fine. This one's going to go smaller and smaller and smaller because they're products. Every time you multiply it, the thing gets smaller and smaller and smaller. So it has to go to 0. But what's the rate at which they do it? And if you put them both together, something that's going off to infinity, something off to 0, these two rates put together give us our pi over 2. I think that's a fun way to be introduced to these things. But anyway, series and products, so summation series and product series are going to be a big thing to explore still, because this is where we're going. The Clausian function itself is just this infinite summation series, is one way to represent it, of sine of x over 1 of x plus sine of 2x divided by 2 squared, sorry, 1 squared, 2 squared, sine of 3x over 3 squared, and sine of 4x over 4 squared, and so on. Okay, so we add something where we're doing a sine and a division of a whole number, and we're always squaring the number, which you might notice is really close to zeta of 2. If you get rid of the tops, it's zeta of 2. Whenever we finish here, the story will be about this size.
Yeah.
Okay? And what do I mean by that? This is fundamental physics completely.
Yeah.
Completely. And when it's right, it implies chemistry completely.
Okay.
That's what the next step is. So, right, getting this right means we can naturally step to getting chemistry right, and so on. And it feels we're definitely on the right direction. So more eyes and more attention, but more focus is what's really important. It's not masses, it's directed focus on figuring out the pieces that need the best fit. So here, as far as I've carried it, if you think this part's all makes perfect symmetric sense, but something over here doesn't, that's where you would start, right? You would go search for your own best answer for these constants, and you know how to scientifically tell whether it's better than the one I have. Because at the end, you compare it to the measurements and tell me the sigma measurement compared to my sigma, and this is how we rate them. Well, two ways we rate them, the sigma and how short your equation is. If you can get a shorter representation that looks more beautiful, condensed than mine, and its sigma is better or equivalent to mine, I definitely consider it. I do this all day. Yeah, so that's where we're at. You guys can completely contribute.
Again, a modicum of this is true. This is revolutionary. That's the thing. Now we actually have a formula prescription. We're actually deriving about what's actually going on.
Yeah. Making sense of the quaternion bound of the external domain, that's a help. Making sense of why each constant has its value lets you look into it and say, I understand the action that's making it now, which then gives you the ability to start understanding, oh, there's a boundary here that should look a certain way, and there's a boundary here that looks a certain way, and this one here, and those three are intersecting right here, doing this and this, right? That's what this is meaning in every single case. So as we learn to tell that story, we're going to literally understand things that we couldn't have guessed were there.
Yeah.
Cool.
Yeah.